Hey guys, Mr. Kennedy back with another video, and this one is on population ecology. Now, when we talk about the population, a population is a group of individuals of a single species. So cats, dogs, humans, frogs is on the first picture. Now, we often talk about the density of that population, and when we talk about the density, we're talking about the number of individuals. You know, New York City is far more densely populated than the small little town that we come from here in Beulaville. It's not going to be static because it's not going to stay consistent necessarily, because you're going to have not only birth rates and death rates are going to change the density of the population, but also things coming into and out of by immigration and emigration are going to affect it. And finally, there is going to be dispersion, which is the space among individuals in a population. There's three basic types. There's clumped, uniform, and random. Now, a clump pattern is here. This one is clumped. You can see how organisms maybe grow in a certain section. This could be because, like in plants, if there was more of a certain element in this area than other areas, so it's going to be more receptive to them. If it's an animal, then maybe it's because there's certain resources that they need there. The next one here is uniform, when they're evenly spaced out. A lot of times nesting animals have uniform distribution or dispersion, in which they separate themselves, and territoriality does this sometimes too, in which they evenly disperse, which makes sure that everybody has what they need. And then there's just simply random, which is just wherever it may fall, right? When we talk about populations, we have to talk about demographics. Demographics is the study of populations and how they change over time. Now, one such thing is a survivorship curve, and the survivorship curve is over here on the right-hand side. And basically what this shows, it shows the number of individuals and how long they live. The number of individuals are over here on the right-hand side, and you notice they all start out here with 1,000, and the percentage, the maximum lifespan. So let's look at the first curve down here, curve 3 by the clams. They have a high number of individuals to begin with, but for some reason they live in an unstable environment and they have very few that live for a long time. And we start at curve 1. This is like the human population. We have a high number of individuals that live for a long amount of time, but the older you get, the fewer and fewer we have. And then you have a population like the squirrels here, curve 2, which actually is a consistent decline as the age of the animal. Now, we often use these survivorship curves along with what's called reproductive tables to talk about the demographics of a population. Now, so survivorship is how long they're living, and then reproduction is how many organisms they're actually producing. Now, in an ideal environment is one that has maximum amount of food, shelter, water, any provisions that a population needs. It has no limiting factor whatsoever. The population will grow exponentially. Now, what exponentially means, it will grow uncontrollably. For example, this equation up here says the change in population size is equal to the birth plus the number of immigrants, the number coming in, minus the deaths, minus the immigrants, the number of leaving. So if we wrote it into a simple equation, we could say the change in the population size divided by the change in time is really equal to births minus deaths. Now, this is an example of what an exponential growth curve looks like. It's what we sometimes call a J-shaped curve, and you can tell why we call it a J-shaped curve, right? Kind of looks like a J. An example of this is it grows very rapidly, and humans are an example. Another growth curve is logistic growth curve, and this is the one that's not in ideal conditions. But as you can see, the logistic growth curve is the S-shaped curve. It's the red line here. But even the S-shaped curve starts out as a J until it reaches this line here. This K represents the carrying capacity. This is the maximum number of individuals an environment can support indefinitely, forever. And we've got some mathematical equations over here we don't need to be too concerned with, but it's basically saying the change in the number of the population divided by the change in time is equal to 1 times the population itself, and this is exponential growth. Now, logistic growth, you actually add in the carrying capacity, which is 1,500 here. It can't go over 1,500, so if you notice, if it has 1,500 in for N, that's the number of the population, then this number would be 0, so it's going to stop growing, which means it would be at this line here. Now, this is kind of a misrepresentation, because what happens is it actually goes above the carrying capacity line and then bursts outnumbered deaths, and it falls below. and actually flux back and forth above and beyond the carrying capacity line, which is called a dynamic equilibrium. But this is a logistic growth curve. Every population in the world grows in a logistic growth curve. Human beings are the only one that haven't reached our carrying capacity yet. We don't really know what that is, and that's really a concern of scientists to know how many individuals the planet can actually hold. Now, when we talk about these life histories and evolution of organisms, organisms have developed two types of reproductive patterns depending on what they see most fit. One is called semal parity, which is a one-shot reproductive stage. Salmon are an example of that. They're born, they go off, they come back, they reproduce one time, and then they die. Another one is an heteroparity, which is a repeated reproduction. Humans are one, rabbits are an example. They repeat over and over again. Now, when we look at these two, what contributes to which one we actually use is going to be the survival rate of the offspring and the likelihood of the adult reaching survival to reproduce. So if you have a very low survival rate of the offspring, you're living in an unstable environment, you're probably going to do semal parity. If you have a stable environment, then you're going to have probably fewer offspring and you're going to do heteroparity. So it kind of makes sense. If you're in an environment that's going to change very quickly, you want to produce a lot of offspring, hoping some of them will live. If you're in an environment that's pretty stable, then you can put more energy into the ones that you produce, and because you know they're going to be able to survive. So there's some trade-offs. If we choose semal parity, then the size of our offspring and the number of offspring are going to be different than if we go heteroparity. Because if we're going to be in an unstable environment, we're going to produce a lot of offspring. They're probably going to be very tiny, right? Such as mosquitoes, for example, because a lot of them are going to be dying. Now, if we're in a situation where it has a very stable environment, we want the one that we produce to be one able to outcompete all the other ones, such as the Brazil nut tree. You can see it right here. This is the Brazil nut tree right here. That the Brazil nut tree packs a lot of nutrients into its seed, so it gives its plant a head start amongst all the rest. So it's able to grow larger and bigger than the rest. So there's trade-offs depending on what life history pattern you choose or you're chosen. All right, oftentimes ecologists have tried to figure out a connection of traits at different population densities, such as using K selection or R selection. Now, K selection is whenever the population is very near the carrying capacity, hence the K, and there's a very high competition for the resources that are there. So you can think of a forest that's very mature. The plants that are there have the K selection because they're able to compete or outcompete other species. Now, R selection is going to be a density independent factor, which set selection, in which it's not affected by the density of the population because it's so low down on the scale. It's nowhere near its carrying capacity line, and there's very little competition. Now, these two have actually sparked people to do further research and to start looking into other factors that regulate population growth, such as density independent and density dependent factors. Now, a density independent factor means it's going to affect every population the same, no matter the size, no matter if it's New York or a tiny little town like we have. Density independent factors would be things like disease, hurricane, natural disaster, things like that. Oh, I said that wrong. Density independent would be hurricane, natural disasters, things like that. A density dependent factor would be disease. So make sure you get that. So this would be like natural disasters. I actually said that wrong. So natural disasters. This would be like disease. For example, when you're in a more densely populated area, disease spreads more quickly than it does in a less populated area. That's why a lot of us didn't get sick until we went to school, when we started being around all those snide-nosed brats, right? Now, another link to this is population dynamics. We just realize no matter which population you look at, eventually you will see fluctuations in the population. One such curve is what we call predator-prey relationship down here at the bottom. And it shows as the number of predators go up, number of prey go down. As the number of prey go down, then the predators go down because what they eat has gone down, which causes the prey to go back up. It's a relationship in which the predator-prey continues to flux up and down. But all populations do this. They flux up and down. Okay, let's think a little bit or talk a little bit about human populations. If you look, this is the human population growth curve. And for about, 1,650 years right here on down this way, we were right at around 500 million people. Then all of a sudden it started growing exponentially. If you'll look, we hit 1 billion people about, let's say, about 1830 maybe. Then we hit 2 billion people around 1970, 3 billion people, or maybe not 1960, 1970, 3 billion. Now look where we are today. We're actually a little bit even further than this. We're about 7.4 billion today. So we're growing exponentially. So if you look at it on a curve like this, here we are. Oh, sorry. So if you look at a curve like this, we're up in this point on this red curve, but this often leads us into what's called demographic transition. And this is talking about how populations or groups of individuals, their ideas or their culture changes over time. If you look, if a population is in stage 1 of demographic transition, they have a very high death rate and their birth rate is very high as well. The population size is usually small. These are in countries that are underdeveloped. And they need a lot of children to help to work on farms, etc. As the country develops, you have early expanding. The birth rate still stays high because people do not realize that the death rate is going down, and they're still in that mentality that they need to have a lot of babies, and that causes the population to grow dramatically. When you get to stage 3, then finally the idea of controlling the amount of people in the family starts to come through the culture. So the birth rate goes down, the death rate is continuing to go down, so the population still continues to go up. Low stationary, you have a very low birth rate, low death rate. The population starts to level off. And this last one, declining, is one we're still looking at. It's believed that eventually the death rate levels off and the birth rate will even go even lower than the death rate, which will slowly cause the populations to decline. This is still theoretical. It's not happened. Here's some countries. Germany is one that we think, you see, it has a very low birth rate and a low death rate, and it's slowly decreasing. Examples of this one in here is the USA, the Japan, France, UK. One here is Brazil, in which their culture is slowly changing to understand that they don't have to have quite as many babies because their death rate is so low. Egypt, Kenya, India are examples of this one. And then there are small remote groups that may be found, through different regions of the world that still employ number 1. Now, the last thing I want to show you is a thing called age structure. And scientists use this to determine what a population is doing, determine if it's growing, declining, or staying very consistent. If you look over here at this one, basically what we have number of males and females within certain age groups. These are different age groups. The blue represents 0 to 14, the green's 15 to 44, and on up. This is really the pre-reproductive years, the reproductive years, and the post-reproductive years, if you think about it. So if you have very few people up here that are old, and you have a lot down here, then the population is growing pretty quickly because these are eventually going to move here and these are going to move here. Now, this is more of a slow growth. This is like the United States. We have a lot of individuals here, but they're getting closer to being equal, right? And then this is where zero growth, where you basically have all the categories exactly the same. So that's an example of age structure and how a demographer might use that in order to determine what the population is doing. Okay, I hope this helps you a little bit on population growth, and I will talk to you soon.